Thank you very much for the invitation. It's a pleasure to be here. So what I'd like to talk about is something that I've been working on for some time with my collaborators, Thomas Hausel and Emmanuel Letelier. And I'd like to start with a somewhat a provocative question that thinking about trying to explain this to people that don't work in the area. What it means is our universe continuous or discrete? Well, I mean, maybe 50 years ago, everybody would agree it was continuous, but I'm sure you, especially the younger generation, probably think otherwise. So what I like to discuss is the connection between the two aspects, the continuous and the discrete. So we think of geometry, we think of something, shapes and things that are continuous. We think of combinatorics, we think of something discrete, and they seem to be sort of completely separate, different aspects of mathematics, of reality. But there is a connection between the two, and this is what I'd like to discuss. So to begin with, I'd like to justify completely from scratch why would you ever consider finite fields. If you are an analyst or engineer, you are likely to think that finite fields is what other people do and maybe waste their time. But again, all of that is changing. When you talk about engineers today, it's no longer necessarily building bridges, but a lot of other things. And finite fields play an important role. So I like this topic because I had a course when I was an undergraduate, which I thought it was really nice, which is completely axiomatic projective geometry. And of course, all of this has a long history in Italy, so it's very pertinent, I think. So if you think about the projective plane, you can think of it in a completely abstract way. And so at the very least, you should have a set of elements that you call points and a set of things that you call lines. So a line should consist of points. So the elements of L are themselves subsets of A, which is a set of points. And what would you like these points on these lines to satisfy? Well, at the very least, we should have that two distinct points lie in a unique line. And two distinct lines should meet at a unique point. And then to avoid completely trivial cases, you should add another axiom. And I'll just say quickly that there are 4 points, not 3 in a line. But it doesn't really matter. Something extra to avoid some complete trivialities. And what I like to emphasize is that this is the sort of minimalistic thing that you expect a projective plane to mean. And you can start working with these axioms and start trying to develop the entire geometry of a projective plane. And you can go very far. And the point I want to emphasize is that there's no need for the set of points A to be finite and to be infinite. So you can perfectly well develop the geometry of these axioms as far as you can take them with a collection of points that is finite. And in fact, Fano, in 1892, I don't know if Fano, I forget now, he was in Torino or Milano, investigated what happens in this situation, and he came up with the simplest possible projective plane, which consists of 7 points. So I'm assuming that you're not all familiar with this construction, so let me give you a simple description. So here are 7 points, and now I have to tell you what the lines are. So I'll draw the lines by joining points that belong to the line. So this is one line, consists of these 3 points. So these are other lines, and then there's one line missing, which doesn't look like a line at all, but this is the other line. So this 7 points together with these 7 subsets of 3 points satisfy these axioms. So for all we can see from the axioms, this is a projective plane that should behave just the same way, the projective plane that we study when we study things that come from, so to speak, reality. So the standard way to study these things is that you define the number q when you have such a finite projective plane to be so that any line has q plus 1 point. So this example of Fano, q is equal to 2. Every line has 3 points. Now, when you follow this axiomatic idea, you try to prove every theorem of projective geometry that you know, and you encounter the first problem, which is that something called the Desargues theorem is not a consequence of these axioms. So Desargues is some configuration of points and lines that you do all these drawings that at the end of the day these 3 points should lie in a line. Well, that's not necessarily true in complete generality with just these axioms. But if you add it to your list of axioms, if it is true, then what you discover is that you can use the purely axiomatic approach, just the axioms, to put coordinates. Then you can put coordinates in your geometry. And what that means is that you can start adding vectors or making sense of multiplication by scalars. And so if we now suddenly have scalars to talk about and our geometry is finite, that collection of scalars must be itself finite. So the scalars, purely from the geometry, get the structure of a field in the sense of algebra. Scalars you can add, you can multiply, you can invert this to non-zero, and so on. And in this setup, you find this now set of scalars is a field which has q elements. So the point I want to make is that starting from what seemed the absolutely minimal requirements for something to be a projective plane, plus this mysterious de Sargues theorem that anyway you might as well just have, you come up with this set of scalars that satisfy everything about scalars that you know, but it happens to be finite. And so geometry now has a life in a completely algebraic setting, but where the scalars are no longer the real numbers or the complex numbers, but are finite. So just to give you a sense, the same plane given in terms of coordinates. So now the coordinates in the case of Fano come from a field of two elements, so they're either 0 or 1. And so you get these 7 possibilities. In fact, there is a book by Harshon which does this whole entire synthetic geometry, axiomatic geometry from first principles. That is an interesting book, which is what I used they were using in the course I took. So if we continue with this idea of geometry, that we could consider in a finite context, we go beyond projective plane, we consider algebraic varieties. So, that is to say, things like this, we have a collection of polynomials, and we're interested in their common zeros, where the coordinates, the zeros that we're looking for, belong to some few k, which typically would be, say, the real numbers or the complex numbers. And these varieties have, well, we get a geometric sense of them. They describe sort of objects that we can imagine existing in nature. But if the polynomials f1 through fn have, say, integer coefficients, which could very well be the case, and if you think of this as something coming from some kind of experiment, you could imagine approximating them. So it's not such a far-fetched assumption, making them rational numbers and then scaling and having them integer coefficients. Then you can also make sense of the collection of zeros. So this is already X. We can talk about its complex points, the solutions of these equations over the complex numbers, or we can consider the same over some finite field, the ones that we encountered before. And so the question between discrete and continuous maybe can be formulated as to the connection between the complex points and the finite field points. So what's the connection between these two things? And let me give you a personal story, which I thought it was quite interesting. When I was in the United States, I got a call from a radio program that they wanted to do some sort of long program interviewing Hispanic scientists. And this was a pre-interview. The pre-interview lasted about an hour, and this person would just not let me go. She really wanted to know what is it that I did every morning when I went to my office. And kind of, I think Latin was like, why is it that we pay you? You know, what exactly is it that you do? And, you know, I don't know if you ever had this experience with talking to your parents or your grandparents, your children, as to what is it that you do. It's extremely difficult to explain and let alone try to justify. And so I tried a few things, and but she would just not let go. I mean, buzzwords were just not enough. I mean, you actually have to deliver some substance. So in the end, I came up with what I thought it was a good idea, and she seemed to at least be happy with that. Of course, they never called back, so maybe it didn't go that well. They chose somewhere else to do a... But so my thought was the following. I can try to explain this connection by an analogy, which somehow captures, I think, some of the spirit of what's going on, not the essence, which is that, you know, we have suppose you have somebody's brain that you want to look into, and you rather not disturb the person by putting your hands in. So what you can do is put these rays through it. I don't know if this is actually what happens, but and you pass these rays through the object, and you collect what happens at the output. And then you do this for every possible plane. And this idea of tomography is that you should be able to recover what this object looks like from all of these different sort of slices that you get at all possible planes. So what I thought would be a way to explain this is that here's the object that we'd like to study, but we can't get our hands on because it's too complicated. But we could try taking these slices, which are what happens at a finite field. And then, ideally, we could try to recover the information about the original object from information about all these different planes, so to speak, that we, through these rays to study it. And why would this be something useful? Well, I mean, the quintessential property of this thing is that it's finite, whereas this is typically some complicated, continuous, infinite object. And so, what do you do with something finite? Well, you count. That's the one thing you can do. The pictures, in spite of the picture of the final plane, which is kind of a schematic anyway, a picture of the SQ points of a variety will typically be of no use at all. Whereas the picture of a complex points tends to be useful. You get a sense of, if you can, get a sense of what the variety might look like. So what we're going to do then is, instead of studying the complex points, working in the continuous side, we work on the discrete side, and instead of drawing pictures or other things we do on the complex points, we will count. And maybe not a complete exaggeration that a great deal of algebraic geometry was developed in order to make sense of geometric things about varieties over finite fields. So, for example, just to give a very simple example, if we take something like y squared equals f of x, and to fix ideas, we say f has degree 8, then its complex points, assuming this, we are in a sort of generic situation, will look like a donut with 3 holes. So this is the algebraic curve of genus 3. What happens if we count points instead? Well, what they discovered is that if you count the number of points this curve has, or a curve in general of genus, arbitrary genus G, is that its number of points looks like this, q to the n being the size of the field in question, plus 1, which maybe one should emphasize and write it as 1 to the n, and then minus some other numbers alpha I to the n, and these numbers alpha I depend exclusively on the curve and the field, and have the property that they're complex numbers and they have absolute value q to the 1/2. And this, in fact, is what's called the Riemann hypothesis for curves over finite fields. And as a consequence, the number of points that this curve has. So recall that the number of points a line has on the projective plane is q plus 1. Well, here q has been replaced by q to the n. So this is the number of points on the line over the field of q to the n elements. So what we can conclude from this, a sort of a very special consequence, is that the number of points of our curve is close to the number of points of a line, and the error term, we can think of this as the number of points on the line. So on P1, projective line, and this as a sort of error, and the error is bounded by the sum of 2g numbers that are of size q to the 1/2. So the worst it can be is 2g times the square root of q. So in any case, here we have a bit of a beginning of what happens in general. On one hand, we have this number g that tells us how these complex points on this curve look like. Any algebraic curve, smooth algebraic curve will look like this. Its complex points will consist of, topologically, of some number of donuts put together to G, thank you. Yeah, sorry. These alpha i's do not depend on n, and there's 2g left. Yeah. So on one hand, this number g is all you need to know if you wanted just somehow the overall shape of this variety or these complex points. And at the same time, it happens to come up here when you count points. So the error term is some number between minus 2g root q and 2g root q. So a priori you could tell, and this number will typically be all over the place in this interval, so you could tell roughly what the number g would be if you knew all these numbers, x of x. So just to give a rough connection between this collection of varieties over finite fields and the corresponding complex counterpart. So for example, we can see from here that if the genus was 0, which is to say that the curve is P1, and so there is no hole, it's just a sphere, then the number of points indeed is q plus 1. It can be anything. So, but we would like something a bit more precise. So let me give you a consequence of the vague conjectures that were proved by Deline in 1973, which gives a bit more precise connection than the one that I'm erasing. So I'm going to take a very special case, but a case that is still sufficiently interesting to be worth remarking. So suppose your variety X is smooth projective, which you can take it to mean that if you look at its complex points, it's a compact manifold, is not missing anything. And suppose also that, possibly accepting some characteristics, so I'll just ignore that for the moment, I'll just say that suppose that there is some polynomial C of Q that it only depends on X, doesn't depend on Q, an actual completely universal polynomial, such that when you count the number of points of this variety over Fq, the answer is given by this polynomial evaluated at the number Q. So for example, if X is a line, then C of Q is Q plus 1, as we already discussed. So there's a polynomial that evaluated at Q gives us its number of points. If X is P2, the plane is Q squared plus Q plus 1. So we just for sanity's check, remember in the case of Fano, Q was 2. So we got 4 plus 2 plus 1 is 7. Those are the 7 points that this final plane had. And so on. And in general, Pn, the polynomial is Q to the n, all the powers of Q down to 1. So certainly these varieties satisfy this, but there's a whole more of them. And what's the conclusion? Suppose X is in this situation, then this polynomial has very specific coefficients these numbers B2K are the Betti numbers, which are, if you like, the analog of the number of holes in the case of a curve. If you haven't seen it before, I'm not going to try to do it in a few minutes, but keep, if anything, in mind the idea that they represent something purely geometric about the variety. Sorry? No. Yes. Try to keep the, here's 2k and k. So only the even numbers are non-zero potentially, and the odd ones are definitely 0. So what does this tell us? This is kind of an amazing thing. And this is now a lot more specific connection between these two sides of the story. This B2K is something purely complex a priori, something having to do with the shape of the complex points of our variety, of the manifold, like the number of holes it has in the case of a curve. And on the other, this is a polynomial that all it does is count the number of points these equations have over a finite field. And so this connection is a sort of two-way street. In the following sense, you can go from x of fq to x of c by computing, if you happen to be able to compute this polynomial, then for free, so to speak, you recover the Betti numbers of your variety. And this was early on one of the things that Trevisan himself emphasized as one of the consequences of his conjectures. But surprisingly enough, you could go the other way, and this is the craziest of the ideas, but again, it has been used this way. Suppose you have a collection of polynomials you happen to like, and you compute them by hand on your computer or whatever, and all the coefficients that you can see are non-negative. Well, maybe you can prove that they're non-negative by proving that they count the number of points on a smooth projective variety, because these numbers b2k, whatever they are dimensions of vector spaces, and so they are non-negative integers. And this, in fact, is something that has been used in this form. So, now the varieties for which this precise statement applies to are very restrictive, but nevertheless worth considering. So in particular, for example, for a number theorist, these varieties are the most boring things ever, because there's no modular forms or anything like that. For example, for a curve, the only curves that will fit in this would be P1. So you throw away half the number theory, basically. So what are other interesting examples? The Grassmannian are other examples, and these are the examples I think Vey was advertising. So these varieties, say Kn, consist of k-dimensional subspaces of a fixed n-dimensional space, vector space, that is. So, for example, lines in P2, lines in a two-dimensional space would be P1. So the projective spaces are included in this for k equals 1. And what one can show is that is a nice exercise to prove that the number of points these varieties have over a finite field FQ are given by the Q binomial coefficient. Where n factorial means so they are a Q analog of the usual binomial coefficient. So, for example, the Grassmannian 5-2, which would be the variety, each point of this variety corresponds to a plane, a two-dimensional subspace of a fixed five-dimensional space. And it's a simple thing to work out what this number is is polynomial, and you find that equals this. So, once you know this, we now know that the Betti numbers of this Grassmannian are, the even ones are 1, 1, 2, 2, etc. And so, in this case, a priori, if you just seen this for the first time, it's not perhaps completely obvious that this polynomial will have, first of all, that it's a polynomial, as it is, but also that it has non-negative coefficients. There's another thing that should come to the fore as a property is, although maybe with one example is a bit too much, once you compute a few more, is that these coefficients are symmetrical. And that exactly corresponds to Poincaré duality for the variety. But something more happens, a somewhat stronger property, so we have Poincaré duality, means that the polynomial is palindromic, but there's another property, which is that the polynomial is unimodal, so the coefficients go up to the middle and then come down, following some unspecified pattern. And this corresponds, or is a consequence, of the Hard-Lefschetz theorem in geometry. So there's a very tight connection between properties about the polynomial and geometric properties about the variety itself. And as I said, you can use it in one direction or the other to deduce things about the polynomial from the geometry, or deduce things from the geometry from the polynomial. Okay, so I'd like to now discuss something closer to my own work and see how these ideas can be applied to a problem that, in a certain sense, is very old, and they're problems of linear algebra, which one kind of thinks that linear algebra is all done, but there are things that are actually difficult still. So for that, I'd like to talk about quivers, which if someone knows the translation to Italian, I appreciate it, because trying to discover with Matteo, couldn't come up with it. Quiver is this thing that people used to have where they put the arrows. So it's a nice name for simply something that usually is just described as an oriented graph. So we consist of some vertices, some arrows, could be multiple, could be self-loops, and typically just a finite thing. Finally many vertices, finally many arrows. So this is just what a quiver is, but what we're interested is in the representations of this quiver. And a representation consists of simply an assignment of a vector space to each dot. So finite dimensional vector space over some field that you fix at the beginning, and to each arrow a linear map between those vector spaces. So representation is something very simple to give. You just give these vector spaces and corresponding maps. But when we talk about representations, typically the thing that is at stake is not so much the representations themselves, but how they're related with each other. So one is interested in representations up to isomorphism. So let me, rather than write all the formal definition, let me give you an example. Suppose our quiver is the SG quiver consisting of one vertex and G loops. And G, by the way, is related to the previous G. But it will take too long to connect the two. So what is a representation? Well, we have to pick a vector space for the only node there is. And for each one of these loops, we have to pick a linear map. So if we fix a basis of the vector space V, a linear map is a matrix. So we can think what we have here is simply G n by n matrices. That's all it is. So capital K, say, is our base field. So that's not too exciting, but what we're interested about the G tuple of matrices is we want to consider them up to simultaneous conjugation. So we say that two G tuples are equivalent if there is a matrix, invertible matrix, that if you conjugate all G matrices on one side, gives you the other G matrices on the other. And now it becomes a much more complicated thing to consider. So if G is equal to 1, of course G equals 0, there's not a whole lot to say. What we have is just one matrix, and we want to consider it up to conjugacy. And that's Jordan's problem, and Jordan brilliantly proved it, and we all studied this in linear algebra, and we know how to describe all possible matrices up to conjugation if we just have one of them. If we have more, things become complicated, and in fact, essentially impossible to do in a reasonable way. So, what does this have to do with the previous discussion? So, Victor Katz in the 80s had the impulse of consider the problem over a finite field. And when you pass to a finite situation, what you can do is count. So here, the natural variety or algebraic object you will consider is kind of horrible. So what, if any, of the previous ideas will apply remains to be seen. But you can still consider this as a purely combinatorial problem. You can count how many such representations, or rather isomorphism classes of representations there are over a finite field. So now, since you can take direct sums of representations, you might as well consider things that you cannot decompose as direct sums. Might as well stay with the building blocks. But then you have the issue that maybe something is indecomposable in your ground field, but it becomes decomposable if you pass to a bigger one. So what you consider then is things that don't behave that way. So things that are absolutely indecomposable. So for example, if we have G equals 1 over there, and we have this matrix, and our base field is the real numbers, then this is indecomposable. You cannot write it as a direct sum, but it is decomposable if you pass to the complex numbers. So this is not an absolutely indecomposable representation. Anyway, to study, we kind of don't want to mess up with our field interfering, so we want to try to stay with extending the scale as much as needed. But since we work on over a finite field, we have to make this distinction. In any case, what Katz considered was, for a given quiver, the number of absolutely indecomposable representations of a fixed dimension, right? So you fix the dimensions of your vector spaces at each node, and you count how many representations up to isomorphisms there are. And if you ever try to do anything like this, you'll see that it becomes kind of messy very quickly. But what Katz proved, that this number, say alpha is the dimension vector, so alpha I is the dimension of the vector space at the node I. So this is the number of absolutely indecomposable number of these things. It's a polynomial in Q. That is to say, it's given by a polynomial that's independent of Q, that depends only on the quiver and on this dimension vector. And he computed presumably a bunch of these cases, and he discovered what, as we were saying before, that all the coefficients seem to be non-negative integers. And he conjectured, in fact, that the coefficients of this polynomial are non-negative integers. Now, to prove, he himself showed that the coefficients are integers. The trouble is to show that they're non-negative, which is a much more difficult thing to do. So just get a sense of this, let's consider the Jordan quiver of one loop and one vertex. What's the polynomial? Well, here there's only one thing to give, one dimension to give, some number. Well, let's call it n. It's weird to call n integer alpha. So, and a isomorphism class representation is simply a matrix, n by n matrix after conjugation. And we don't want it to decompose into direct sums after passing to a field. So what's the possible indecomposable matrix? Well, we know it's a sum of Jordan blocks if we go to a sufficiently big field. So we might as well just have only one block. And since we're working over some finite field FQ, the Jordan block will have to be sort of an n by n Jordan block with the eigenvalue in this ground field itself. So we have exactly two choices for any n. For every n, the answer is the same. Okay. So, just as a side remark, if you haven't been thinking about these things for some time, you may be tempted to think, for example, I'll give it you as a challenge. If you count in the number of points of something algebraic, something described by zeros or polynomials, you cannot have it that the answer is given by a polynomial that has rational coefficients, actual denominator. And so I think I'll skip it, but I'll leave it for you to think about. So suppose you take something like the affine line times the affine line minus the diagonal, so pairs of distinct scalars, and you mod out by the involution that swaps the two. Okay, let's call this x. The first impulse, perhaps, is to say that the number of points of this is 1/2 of q times q minus 1. Which looks like it has actual denominators, although every time you plug in a q, you'll get an integer out. So it's conceivable that is the number of points of something. It's certainly the number of points of pairs of a element of A1. But this, in fact, is wrong, and the number of points is the polynomial with integer coefficients. So the issue of being integer coefficients is somehow built into the way this whole machinery of algebraic varieties with finite fields is constructed. The fact that the coefficients are not negative, it not always works. Okay, the number of points of this thing is in fact q times q minus 1. Or if you take p1 and you subtract 10 points of it, you will have q minus 9 points. So the coefficients being negative is not something completely easy to visualize why it should happen or not. Okay, so I'm running out of time, and I gravely overestimated what I was going to be able to say. So let me try to cut to the chase. And to say that Crowley-Bobby and van der Berg proved this past conjecture that I mentioned, assuming that the dimension vector alpha is indivisible, that is to say, is not the proper multiple of any other dimension vector, and the proof uses a variety, which is a variety studied by Nakajima, and whose number of points is precisely this polynomial A of alpha. So with Letellier and Hausel, we extended these ideas to all dimension vectors alpha. And in the few minutes I have, let me give you just a flavor of the kind of things that happen in this game. I mean, something I like now to give you something completely combinatorial. But again, going back to the beginning, this combinatorics has a geometric consequence. So let me very briefly tell you how could you compute this polynomial in practice if you really had to. It's not easy. So let me give you an example where the quiver is this, which I call the hedgehog. So it consists of one vector space at the middle, and then k short legs come out with a 1 at the end. So the dimension vector is n here and 1 all around. So I never talked about the orientation of the arrows too much. The point is that this polynomial is independent of the orientation. But so let's say we orient all the edges in. So what we have here is maps from the field to a vector space of dimension n, k maps. Okay, so if I fix a basis of my vector field on my vector space in the middle, then each map gives me a column vector. So I can describe this representation by saying that I have k n dimensional vectors. Okay, and now the isomorphisms happen where we can act by GLN on this vector space and GL1 on each one of these. So GLN acts on this side, and each one of these acts GL1. So, and now we can use what I like to ascribe to Nick Katz, although I don't think he ever said it in this context. We can apply the miracle of transposition. So instead of looking at these columns, I can look at these rows. And I forget the GL1 for the moment. I have GLN acting. So what this gives is a point in the Grossmannian of an n-dimensional vector space inside a k-dimensional vector space. And I can use this GLN to put my matrix into row echelon form. And then this will be really quick, but I want to finish in 1 minute. So let me give you an example. Suppose my row echelon form, so we're going back to linear algebra. It's all linear algebra. Looks like this. So I'm doing 5, 2. So K is 5, N is 2. So I have a 2 by 5 matrix. Suppose that my row echelon form looks like this. And I think this is backwards from one used to study, teach in the US at least. So zeros go to the right and down. These are the pivots. And the stars are anything. So this is what, for example, a representation of this quiver looks like. Once I put it in row echelon form, it's uniquely determined. So the question is this echelon form, does this representation, by choosing different values for my star, is it indecomposable? Because I want to count indecomposable representation, not just representations. Otherwise, I would just be counting points on this Schubert cell. And so here's one way to do this. As I say, this is really extremely quick. Allow me just to finish this thought. So I put the pivot is on row 3, column 3, and this pivot is on column 5. So I can draw a graph by putting where the stars are. Okay? And then if I look at an actual representation that ends up in this cell, so the stars have some specific value, if a star is there, so some number in here is non-zero, I consider the corresponding edge. And so the beautiful thing that happens is that indecomposable representation corresponds exactly to the graph. So it's a subgraph of this being connected. So what happens then is that you end up counting indecomposable representations by counting connected subgraphs of a bunch of graphs indexed by these Schubert cells. And so this gives a way to handle at least some of these mysterious polynomials. I have to stop here. Thank you.
So you get to each quiver, so you get a corresponding algebraic variety.
Yeah, this Nakajima quiver variety.
Yes, and this is independent of Q, I guess, of the or
is associated to the quiver and the dimension, vector.
Dimension, but not to the
field. No, it's
something
yeah.
That, okay.
And the number of points of this variety is this polynomial of Victor Katz.
Okay.
But that is actually not an easy thing. I mean, because the connection between the two things is rather exotic. It's difficult. So it doesn't come from the thing this thing actually is counting. We have to do some crazy geometric game to get to this other variety.
And the representations correspond like to rational points of this, and then so you explain everything in terms of the zeta function of this.
Yeah, except that there's one other thing that I didn't mention, which is the variety is smooth, but it's not compact. So you have to still also prove that the mix or structure of this variety is pure, which is yet more to do.
So what type of varieties, did you get? So these are Rosmanians, so we know them. Like, what
well, I mean,
what type of more exotic
I think,
varieties?
I see sort of two possible answers. I mean, the Nakajima Koi varieties are all hyperkähler. They can also give them as sort of symplective reduction of moment maps. So they live in the world of this symplective reduction, hyperkähler manifolds. The varieties that have a polynomial number of points, I think, are very strange. I don't know if there's any hope to try to understand them in general. And I think it's misleading to think that they're simple, they're easy. So, for example, one example that I find I like very much and it's very intriguing is the nilpotent cone. If you look at all the important n by n matrices, then the number of points is q to the n squared minus n over fq. But the variety is singular, is certainly far from being affine space, as far as I can see. So I think that there is a whole bunch of varieties that are much more mysterious that also have the property that the number of points is given by a polynomial. But I'm sorry, I don't have anything else to say.
But you are more interested in the cases where the zeta function is a polynomial, not a rational.
I mean, it's just that we're interested in my collaborators on the geometry of these varieties. I didn't say what they are. I mean, I actually mentioned in the abstract that I switched gears. I didn't talk about them. But the ultimate goal is to, for example, compute the Betty numbers of the modular space of Higgs bundles. Of the modular space of Higgs bundles on a curve. And that it's maybe doable. But what we did is, instead of looking at that specific variety, this is also a hyperkähler manifold, and you can change its complex structure. And if you do that, it becomes a character variety, which is also an algebraic affine variety. And there we can count the number of points. As it happens, the number of points is polynomial, so great. That means that there's a lot of things that are simpler. It's not like we were looking for varieties with polynomial counts. I mean, our ultimate goal was to get to the Betty numbers of the modular space of Higgs bundles.
Are you saying that the modular space of Higgs bundles is what?
No, I'm not saying that because, in fact, it's not true. So the modular space of Higgs bundles depends strongly on the complex structure of the curve, whereas the character variety does not. It's only representations of the fundamental group, so it's purely topological. But what happens is the two varieties are diffeomorphic. So in terms of their Betty numbers, you can study one or the other. So our approach was to say, okay, we want the Betty numbers of this. We switch gears and look at in this other complex structure, we can study this variety instead. And this happens to have polynomial counts. The other one, its counterpoint depends strongly on the actual curve. So you need, the data of the curve has to come in.
You said that the Nakajima variety was hyperkähler, so why does it have polynomial number of points?
I think it's a good question. I always suspected that there's a connection between the two facts, but I don't know how far one can push it. The connection is not clear to me of the two facts, hyperkähler and polynomial count. But it may be there is a connection, I just don't know. K3 surfaces don't have polynomial count necessarily, right? And they're hyperkähler. So there's something. If there's something, one has to be careful of what the statement may be. Thank you.